Hello, Mark. Thank you for presenting again today. Please tell the audience shortly about your role inside KEMET, and then you can start your presentation.
Hi, Alexander. Yeah, again, my name's Mark Laps, ceramic innovation center. So I've been here for about 10 years. Started out as a test engineer, and now I'm a technical product manager here in ceramics. So mainly involved with bringing new products to market, technical seminars, trainings, and providing technical content to customers and webinars like this. So with that, we'll go ahead and get started. So today's webinar is high voltage ceramic capacitors, and let me see if it's transitioning. There we go. All right, so today we're going to talk about what is high voltage when we're talking about capacitors, some basics on MLCC design, creepage versus clearance, what is that and what is the differences, what causes arcing, what is arcing, and what KEMET does to prevent that, including KEMET's ArcShield technology, and then review a little bit about KEMET's high voltage portfolio. All right, so what is high voltage when it relates to capacitors? Now, the answer is it really depends, since high voltage is really kind of a loose term. It depends on the type of capacitor that we're talking about. For example, what's considered high voltage for ceramic capacitors may be different than a tantalum capacitor, which also may be different for an electrolytic capacitor. It also depends on the capacitor supplier. For example, one supplier may consider high voltage to be 630 volts and above for a ceramic capacitor, while another supplier may consider it to be 500 volts and above for ceramic capacitors. So you really have to think about when you go and search for high voltage, what the supplier is actually calling high voltage. Now, for KEMET, we specify high voltage as greater than 250 volts for DC-rated ceramic capacitors, and equal to or greater than 250 volts for AC-rated capacitors. So when reviewing KEMET's literature and data sheets for high voltage products, keep in mind which voltages correspond to low voltage and which voltages correspond to high voltage. Okay, so before we go into detail on high voltage, let's review basic MLCC design. Now, MLCCs are constructed using alternating layers of ceramic dielectric with metal electrodes. Each layer represents a single capacitor, and adding additional layers adds more capacitance to the MLCC since they are in parallel. We calculate capacitance using the capacitance equation as we can see in the slide. Now, by looking at the parameters, if we increase the dielectric constant, the area of the electrodes, or the number of layers in the capacitor, we will increase the capacitance. We can also choose to reduce the dielectric thickness since the capacitance is inversely proportional to the thickness. Now, if you were to reduce the ceramic thickness in half, it would theoretically double your capacitance because you could put more layers in the MLCC structure. All right, so one of the primary concerns when operating these capacitors at high voltages is the risk of arcing in the application. Surface arcing is the electrical breakdown between the two MLCC terminations or between one of the terminations and the internal electrodes of the capacitor within the ceramic body. It occurs most frequently in applications above, say, 300 volts and is heavily influenced by humidity, surface contamination, and where there's minimal separation between the two termination surfaces. This is also referred to as the creepage distance. This phenomenon can either damage surrounding components or lead to a breakdown of the MLCC dielectric, resulting in a short circuit condition and catastrophic failure. Now, before we go over what causes arcing, it's important to understand a little bit about creepage and clearance distances, since certain applications require minimum creepage and clearance distance separation. Now, creepage is defined as the space between the conductive elements through the insulative surface. Creepage follows the path from one conductor to another through an insulative surface, which may have turns, bends, and even gaps. Clearance is the spacing between conductive elements through air and can be thought of as a line of sight distances between 2 points. Now, these definitions apply to all electronic components and even printed circuit board traces that have 2 or more opposing electrodes. Since the distance between the two conductors drastically affects the voltage at which an arc can occur, the minimum separation distance for the creepage and clearance depends on the application voltage and critical nature of the circuit. Now, for MLCCs, the creepage distance is the distance between the two end terminations, since they are the outer opposing conductive elements. Now, since there are no protruding conductive elements, the creepage and clearance distances are pretty much the same. For the next few slides, we're going to review the phenomenon of surface arcing for ceramic multilayer capacitors, or MLCCs. Now, when voltage is applied to an MLCC, a potential difference is established between the opposing termination and opposing electrode structure. Now, because there are alternating layers of electrodes within the MLCC structure, there will be opposing electric polarities between each electrode. And now in this slide, we've shown the opposing termination and electrode polarities with red positive and blue negative signs. This opposing polarity produces an electric field between each electrode layer. As the voltages increase across the MLCC terminations, the magnitude of the electric field increases between the electrode, and the voltage is increased, and as the voltage is increased way beyond the rated voltage, the MLCC will eventually undergo a dielectric breakdown. Okay, so for this slide, we've removed the positive and negative voltage symbols in the inner electrodes to really focus our attention on the outer electrodes of the MLCC. Now, for some high voltage MLCCs, as the voltage across the terminals is increased, there's an electric field concentration and is localized in the termination area of the first counter electrode of the MLCC. This difference in potential begins to build along the surface of the chip, and the air begins to ionize. Now, by continuing to increase the voltage, the MLCC will reach what's called the inception voltage. The inception voltage is the voltage in which the ionized air begins to conduct electricity. When this occurs, the conductive path is created along the ceramic body, allowing the energy in the concentrated electric field of the termination area to discharge. The discharge of energy travels through the air along the surface of the capacitor. Now, during the discharge, there is a visible and audible electric arc across the surface of the chip. Now, it's important to note that some high-voltage ceramic capacitors can arc at applied voltages less than the rated voltage of the capacitor, and we'll see how to get around this issue in the next few slides. Now, in the previous slide, we showed how arcing can occur between the two terminations of the MLCCs. This slide shows that the arcing can occur between the termination and the actual internal electrode structure. When this happens, instead of arcing across the surface of the MLCC, it travels from the termination of the MLCC to the first opposing electrode, causing a dielectric breakdown. Now, here we can see the difference between the terminal-to-terminal arc versus a terminal-to-active electrode arc. On the left, we see a terminal-to-terminal arc resulting in carbon traces between the two terminations, which can result in a lower insulation resistance. And on the right, we can see terminal-to-active electrode arcing, and that can achieve dielectric breakdown and a catastrophic failure. Now, there are three possible solutions for MLCC surface arcing. One, suppliers have used surface coatings, and this is added at the supplier, not the end customer. It adds an additional process step, and it's really critical that there's no damage to the air gap underneath the coating. You can do PCB coatings added after the PCB assembly. It does add a process step. It adds cost, and really once you apply that coating, it's very difficult, if not impossible, to do any real rework on the PCB. Another one is a serial electrode design. This reduces the electric field strength. Available capacitance in the MLCC package is lowered since those are in series. It does allow for much higher voltage capability and reduces the probability of MLCC failure due to flex cracks, and we'll show that in the next slide on why that is. Another one is ArcShield technology, which reduces the electric field strength, reduces the ionization of the air at the MLCC surface, and maximizes the available capacitance in the MLCC package size. And we'll go over details of these next few slides. Now, some capacitor manufacturers have turned to coating technologies like we talked about. Polymer or glass coatings are applied to the surface of the chip to fill those voids and provide a smooth surface with better creepage distance capability. Now, filling in these voids with insulating material also reduces the potential for the entrapment of contaminants, improves the dielectric stability across the surface of the chip. Improving this stability reduces the ionization of the air, increases the inception voltage along the surface, thereby reducing the potential for arcing and improving the voltage performance of the capacitor. Not only does this add a cost to the process, care must be taken not to damage the thin coating on the MLCC, which exposes the dielectric to air creating an opportunity for the ionization and arcing. Now, designers have used surface coatings on PCBs and high voltage applications for decades. It's proven technology that does improve the performance in high voltage applications. Now, the primary disadvantage, again, of this technology is the additional process step and cost, and it's sometimes necessary to meet safety standards. Most designers choose to avoid this costly measure whenever possible. Another possible solution when choosing an MLCC is with a serial design for high voltage. Here we can see a standard 1 microfarad MLCC rated at 1000 volts. Now, if we put 5 of those MLCCs in series, the total voltage capability is now 5000 volts, but the overall capacitance is reduced to only 220 nanofarads. In a serial electrode design, we're doing just that. Each of those capacitors can be manufactured into a single monolithic structure, and is effectively 5 capacitors in series. And you can see here that some of the electrodes are now floating, which is where the term floating electrode comes from. So by using this structure, you can get much higher voltage capability in a single high voltage MLCC structure. Now, KEMET offers serial electrode or floating electrode designs, which utilizes a cascade internal electrode design configured to form multiple capacitors in series within a single device. Effectively, there are 2 individual capacitor elements in series in a single monolithic structure. Serial electrode designs are very common in high voltage MLCCs and are the predominant method for obtaining voltage ratings greater than 1000 volts. In fact, as MLCC ratings start increasing above 1000 volts, it's common to see a higher number of cascading electrode designs, such as 3, 4, or even 5 serial designs. Now, because there are effectively 2 capacitors in series in this example, if one were to short due to a crack, the other element would block the DC current and theoretically fail open. Note that the flex crack cannot cross multiple electrode patterns originating from both ends of the capacitor. It can only cross the electrode pattern where it originates from, and there will be floating across the active series. Therefore, these capacitors are also referred to as fail-open technology, which is commonly used for application with potential for high DC currents, such as battery lines. Now, serial designs have 2 or more overlap areas in series between the terminals. The voltage the voltage acting on each of those overlap areas is the reciprocal of the number of capacitors in series, but this significantly lowers the capacitance. This is one of the major drawbacks of serial design MLCCs. That's why KEMET has introduced a new type of design called ArcShield to allow higher voltages without sacrificing capacitance. Now, the shield design has a much larger overlap area, and there's no lowering the capacitance to standard capacitance equation, and that standard capacitance equation, as we saw before, still applies. Since there's no lowering of active working voltage in this area, thickness of the electrodes, so the opposing electrodes, it has to be increased for higher voltage breakdown capability. Now, even though this lowers the capacitance for a given X7R system, the capacitance can be increased up to 4 times more than a serial electrode design. Now, to address flex crack concerns, KEMET has developed an ArcShield series with flexible termination technology. Alright, so now how does this work? When a high voltage bias is applied to an ArcShield MLCC, a potential difference is established between the opposing termination and opposing electrode structure. But the electric field concentration is localized in the shield electrodes rather than the termination surface in respective first counter electrode. This minimizes the difference in potential along the surface of the chip and drastically improves the creepage distance capability of smaller case-sized devices and constructed of high porosity dielectric materials. Now, to go into a little bit of further explanation, you can see here a standard design on the left, and this really has an opposite field that extends close to the termination of the opposed polarity. So there's a low energy barrier in this region right here, so you get a high field concentration between the termination and the first opposing electrode. But in the terminal-to-terminal arcing situation in an ArcShield design, you have this same polarity as the termination electrode extending out towards the center of the chip, and this increases the energy barrier as a function of distance across the chip. So now you don't have this opposing electrode with the termination providing this shield which is why we call it the ArcShield technology for this MLCC structure. So now we can create a much stronger dielectric in the center of the chip, allowing us to create more and more active layers and increase the capacitance without the risk of arcing along the surface. Alright, so if we consider a standard design, in a standard overlap X7R MLCC, there are three ways that you can fail high voltage. Arcing between the terminal and first electrode of opposite polarities, you can see here. Arcing between terminals, as you can see over here. And then internal breakdown. If you go too high in voltage and you don't arc, eventually you will break down the dielectric. Now, the ArcShield can help resolve all three of these. One, by adding the shield to prevent that termination to first counter electrode, which also prevents that ionization of air and creating that barrier between termination to termination, and also allows you to put more layers with a higher thickness to increase that dielectric breakdown. Alright, so this is just a general overview of our ArcShield technology. It's a patented electrode design that suppresses an arc over event while increasing the available capacitance. So the goal here, to remember, is to get more capacitance in a higher voltage MLCC in a given case size. So KEMET has created and launched the world's smallest high voltage MLCC, which is an 0603 package. It's permanent protection, which means there's nothing that you need to do to the part when you mount it. There's no coatings you need to add or any other special precautions. These are available in 500 volt to 1000 volt ratings, in 0603 and up to 2225 case sizes, up to 560 nanofarads. And for anybody concerned with flex cracks, because these are standard electrode designs, they are available in flex term. This is just a brief overview of our high voltage portfolio. KEMET is a leader in high voltage, and we have a multitude of series that really cater up to the 10 kilovolt voltage rating. So we have a vast product portfolio, not only surface mount but also leaded part types for high voltage. We're not going to go into detail of each one of these. You can go to our website and get more information about each one of these high voltage series, but we offer both base metal BME series as well as PME, precious metal electrodes, with tin lead as well. So you can see multiple form factors. We have Gold Max, KPS series, so you can go to our website and find out more information there. Now, we did talk about high voltage being 250 volts AC rated. We do have a portfolio of safety rated disc capacitors, the C900, ER safety, KJ series, and we're getting ready to launch a safety surface mount series, which is 250 volts AC and up to 5 kilovolts pulse capable. We've also launched a non-safety rated 250 volts AC rated that doesn't come with the IEC standard, but it's for non-safety rated applications. So that just goes to show that not only are we doing DC rated high voltage, but also AC rated. All right, but just real quick, before I leave you today, I wanted to show you a little bit about creepage versus clearance when we're talking about a leaded device. So here's a picture of a standard safety capacitor leaded device. Now, as you can see here, the clearance distance now becomes the distance between the lead wires instead of the MLCC terminations that we saw before. Now, the creepage distance is actually the distance, the path length distance, along the capacitor's coated material. So it gives you a better explanation of creepage versus clearance. Now, when you mount this capacitor, that changes. The creepage distance now can be reduced to the distance between the mounted pads, since it's the shorter length than the capacitor's coating. Now, in some cases, even when mounting a ceramic disc capacitor such as this, the shorter path length may be along the ceramic coating and not necessarily in the solder pads. You have to be aware of that. For example, a disc capacitor with small diameters. Now, when selecting the lead types for a safety disc such as this, there are options for straight leads, outside kink, and inside kink. Now, be aware that inside kink wires will reduce the clearance distance and needs to be taken into consideration when using for high voltage applications. So when you look at your lead configuration styles, you have to think about clearance and creepage distances depending on the style that you're going to choose. Now, if you want more information about KEMET's high voltage portfolio, you can go to our Component Edge website. Just type in search.kemet.com and you'll be taken here. Now, you don't want to search for high voltage. Now, again, the term high voltage is a loose term, so we don't actually use it as a search term. you actually just go to the voltage field, as you can see here, and you can select the voltage that you're wanting to see. So once you select your voltage, all these part types will be filtered to that specific voltage that you're looking for. And that concludes today's presentation. I think we can open up to questions.
Yeah, hello Mark. Thank you for presenting. I received up to now 2 questions. Maybe there are some more. So to all attendees, please enter your questions to the chat function on the right-hand side of your browser. So one question is, are high voltage MLCC available with AEC-Q 200 certification?
Great question. Absolutely. Yes, they are. So if you go to Component Edge, you can actually filter not only for voltage, but there's a little field that you can filter for AEC-Q 200 automotive qualified, and it'll give you all high voltage automotive qualified products.
Okay, great. And the second question is, what is the smallest case size for high voltage capacitors?
Right now it's 0603, but we are in development of 0402 high voltage in ArcShield.
Okay. Are there any limitations because regarding creepage and clearance distance for the high voltage or for small size high voltage capacitors?
Well, there are some industry specifications for designers for creepage and clearance, and right now we have to work through that because sometimes you can buy a capacitor and mount it to your circuit board and maybe be in violation of a creepage and clearance spec. But we encourage customers to really consider those specifications and maybe updating those specifications for these new capacitors that are coming in and allowing for miniaturization in high voltage that lets you get away of those limitations of creepage and clearance, because those specifications for creepage and clearance are meant to protect the PCB from arcing. But if you have enabling technology such as ArcShield, you can get around that. So we have to think about how we can get those specs updated to include things like ArcShield technology, so you're not in violation of the spec, but you're actually complementing it.
Okay. So it seems like these are all questions for the moment. And now to all attendees, if you have any more questions. Oh, just received another question, just in the moment. Will we have higher than 390 picofarad in small footprints for 3 kV cap?
I'll have to look at our roadmap. We should. We have a new high voltage series coming out in the next few months of an extension. So we can look at our roadmap, and if you have more questions on the roadmap, we can actually show you what we're in development of. We can share that with our customers and whoever's online here, and you can see what we're going to be launching in the next 3 months, 6 months, and a year for extending those case sizes and cap values in that voltage range. So I can take that one offline and get back to the attendee.
Okay, great. I can give you the contact later. Okay, so thank you for presenting. Thank you to the audience for joining today. If you have any more questions, please contact your local sales, your FAE, or the technical product manager. You can see the email address on the desktop. Yes, and thank you for joining today, and I hope to see you again soon.
Thank you.
Okay, goodbye.